First up, for those of you who attended Dave Johnson's keynote this morning, I used to work for Dave, the Department of Environment, and so that's given me an interest in actually trying to make sure that the science that I now do as a PhD student here at the University of Adelaide is connected as much as possible to some kind of real-world outcome, and that the work that I do can be used by policymakers and land managers across the country. So we've heard a lot about the science behind climate predictions and the predictions that we expect for South Australia. And the next step for that, for me as an ecologist, is start to say, okay, what's the response that we're going to see on the state's biodiversity? How is the biodiversity that we see going to shift under these climate scenarios? And so I've tried to develop a tool to help us predict this future biota. So a little bit of background, don't panic. I'm going to use the word isotope, but it'll be brief. Carbon is present in two forms in the atmosphere, carbon-12 and carbon-13. And these are biologically equivalent. They can both be used by plants and by other organisms, but it is energetically more expensive for plants to use carbon-13, and that's just because it's heavier. They've got to lug around heavier molecules, so they would prefer to use carbon-12 wherever possible. And they can biochemically discriminate against carbon-13. Now the way in which that occurs, the process in which this, I don't have a laser. Okay. The way in which this occurs is the carbon dioxide diffuses into this leaf cross-section. The carbon-12 within that pocket of air is then utilised, and to allow fresh carbon-12 to diffuse in, those leaf stomata through which the air needs to remain open. In an arid environment, that risks desiccation for the plant. The plant will start to dry out, and so it closes the stomata. At that point, it's forced to start utilising carbon-13, and so the ratio of carbon-12 to 13 starts to approach parity in the tissues of that plant. So that means that we can use the ratio of carbon-12 and carbon-13 as a proxy for water use efficiency or stress in these plants. Now, what that means is that we would expect this relationship to develop where that isotope ratio starts to decrease as we move from an arid environment to a mesic environment. And these are just plants. These could be several different species of plants along an aridity gradient. And this dashed line here represents that community slope, that relationship that we would expect to see in these plants at a background level. So, if we have a hypothetical gradient, a transect that we draw from an arid environment through to a wetter environment, we would expect to see several species, which can be represented in the top panel here. These are species that would have more abundance or higher fitness at one point and then be overtaken by a second species with regular species turnover occurring across those gradients. And then, in terms of the isotopic trends that we would see within those plants, we would expect that community slope represented in the grey lines on the second two panels. But the values that give rise to that community slope, that dashed line, could be generated by different species of plants doing different things. Under the second model here, under biotic homeostasis, this has been recorded in Western Australian eucalypts, and this shows very steep slopes of species turnover, regular species turnover, leading to that shallower community slope. And universal scaling, which was shown in some Chinese study on a range of different plant species, we see each of those species slopes representative of a broader community slope. So to explore which of these predominated, we decided to look at a third study here in South Australia. And South Australia is a great study to look at, a great state to look at gradient studies, because we have this fantastic natural gradient that occurs along the Adelaide geosyncline, ranging from a really hot arid environment up in the Stony Plains around Mount Lyndhurst, coming down through the Gammon Ranges, the Flinders Ranges, the Mount Lofties, and to the base of the Fleurieu Peninsula. And this spans roughly an order of magnitude in mean annual precipitation. And along this gradient, we have established 42 permanent monitoring sites. These have been established using the AusPlots rangelands methodology. This is a fantastic program of national infrastructure that I'd encourage you to investigate more about, at which these 1 hectare sites, all of the vascular plants have been recorded, both their structure and identification, and all of that data is available, and the samples that have been collected are available for use by researchers anywhere. I used these samples, I accessed them, and every species of plant that occurred at 4 or more of those sites, those 42 sites, I took a leaf sample, I dried that, ground it, subjected that to isotope ratio mass spectrometry for a total of over 1,000 measurements from 151 species of plants. And that included 12 growth forms, so a range of different grasses and forbs and trees, to test which responses we saw. And in terms of what that looked like, it meant that we saw some characteristic taxa of wet environments down in the south. So the sedges and yuccas were in the southern end of that gradient, moving through a range of trees and forbs, perennial forbs in the middle, and starting to get into annual forbs and chenopods in the northern end of the transect. So we moved from these xeric grasslands or chenopod shrublands right down to these closed woodlands in the south. And here's all of the data. Here's the results. And the first thing that we should take from this is that that dashed line is exactly what we would expect. We see the trend that we thought we would, with carbon isotope discrimination or the approaching parity, or the isotope ratio approaching parity as we get to the more mesic end of that transect. But there's an awful lot of spread around that line. So we'd like to start looking at how those species are affecting that slope and what the individual species are doing. So if we pick out one, and this will be a species that many of you would be familiar with, this is Dianella revoluta. It's a perennial forb. It's often planted in supermarket car parks because it's tough and you can drive your car into it. And this is a really useful starting point, because we see, if we look at this relationship, that the species slope is much steeper than that overall community slope. And that suggests that this particular species is more sensitive than we would expect the average species or the community as a whole to be to aridification. And this species might encounter more rapid turnover than other species under various aridification scenarios. So if we bring in the rest of the data across my different groups, we see a range of responses. Now, this study represented 151 species, and so some of the majority of these species were sampled less than 10 times, and that makes it difficult to achieve significance on all of these relationships, all of these regressions. But we do start to get an idea of the relationships that we might see. So we see, for example, on this yucca here, this species tracks pretty much exactly what we would expect to see on an average plant with that community. But we also see some species that have very, very flat slopes. These can be regarded as pretty insensitive. They don't seem to care what's going on with the climate. We see very steep slopes that go in the same direction as the community slope. These are likely to be the more sensitive plants. And we even see some slopes that are inverted. And these plants run completely counter to our expectations of what they should be doing under aridification. And there doesn't appear to be a consistency across growth forms. We're not seeing all of the annual grasses do one thing and all of the trees doing another. There is, to better display this data and to start to appreciate where this might go, I'd like to present the same data in a slightly different way. This thick black line here would represent a slope of 0. This would be completely insensitive to climate stress. And this dashed line that we've become so familiar with is the standard community slope gained from all of those plants. If we then map those plants based on their slope, with size representing the number of species selected, So a number of species of that site. So that very large blue spot in the middle is the Dianella, which I had 15 samples for, and the smaller dots, there might only be 4 or 5 samples for those. We can start to bin these groups into their sensitivity. So down the bottom here, these are the super sensitive plants that we might expect to be really sensitive and start to disappear very quickly under aridification scenarios. We then have our representative slopes. These are our average Joes that are doing the standard thing that we would expect. These are our insensitive species that maybe we don't need to worry too much about. Maybe these guys are pretty plastic and can survive under a range of scenarios. And these are our paradoxes, our contrary species. And when you look at what these include, they tend to be things like river redgums and trees that may well have deep roots that can tap groundwater and therefore might be a bit immune from a broader climate signal, or species that are really short-lived, and so when they or live in very wet environments. So when there's a downpour, they can grow quickly, and then they die. So what I hope that I've created here is a framework that actually allows us to class species sensitivity. And this is a format that will allow us to start to prioritise and plan for which species and which ecological communities we need to protect. We need to look at helping, maybe watering or targeting for conservation in other ways, and provided a blueprint for how we can further fund this work to make those models more robust. Each species to develop this would cost around $200 to $300, so this represents a remarkably cheap way to actually predict which species might require our intervention to help. And finally, I'd like to look at expanding this work to other aridity transects, to look at its generalisability and its robustness to other climatic zones. So some work's been done in Western Australia and some work in China, but there's lots more work that we could do in those locations and other areas. Thank you very much. I'd like to thank these people and these institutions for their support. Thank you.
Thanks.